This is a short video about section 5.2.1 in Stein's elementary number theory book. And so the last video was about the finite continued fractions, and our notation for them, just to remind you, is this bracket notation a0, comma, dot, 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 up to say some number a sub m. Now, to this point, we're not assuming that these a's are integers, but when they are, remember that we'll call that a simple continued fraction. But just for now, just so we're on the same page with what's going on, if you had something like, say, bracket 1, 2, 3, 4, then remember what that stands for is we're going to do 1, that's this one here, and then now plus 1 over the next number 2, plus 1 over the next number 3, plus 1 over the next number 4. So remember, like, all of that stuff is taking place underneath these successive denominators. So remember, that's what this continued fraction is. Now, the main subject of this video is just this introduction to this idea of a partial convergence of a continued fraction. So it's good to notice n is fixed to be less than or equal to m here. So if you've got some continued fraction, a0 through am, then we're going to define here the nth convergent, or maybe the nth partial convergent, whatever you want to say. So the nth convergent of your continued fraction, a0 through am, is just the continued fraction where, just notice, you cut it off at the index n. Remember, just you cut it off at some smaller index. We'll call that the nth convergent. And there's a recursive formula for how to figure out what the nth convergence of a continued fraction is. And the instructions for how to build it are the following. You've got some sequence of numbers that are p's with some subscripts, and you've also got subsequence of numbers that are q's with some subscripts. And the fact that they start at -2 just makes things line up a little bit better later on, so that we're able to use these sequences to model these p's and these q's rather to model, you know, like the whole continued fraction. The details are like not entirely clear why, I guess why it starts at -2. Anyway, though, just trust me, it's useful. And so what are we going to do to talk about the nth convergent of a continued fraction, a0 through am? We just want to be able to write it as just this fraction pn over qn, where again, these formulas are kind of obtained inductively, recursively is what I mean to say right here. Now, how you prove that this formula works is by using induction. That's where I was getting ahead of myself a little bit. But what I want to do is just kind of illustrate just some of the ideas that are going on here. So for instance, let's say that this is a0, a1, a2, a3 here. So that's my m is equal to 3. And now what if I wanted to tell you about the second convergent of that above fraction? Well, it would just be 1, 2, 3, right? Because this 3 is really in the second spot, because this is a0, this is a1, and this is a2. So that's when n equals 2. And just what is that? It's just 1 plus 1 over 2 plus 1 over 3, right? So again, it's kind of like I just take this part of the continued fraction up there. So that's what we'll call the second convergent. And what we also want to do is maybe play around with this inductive formula a little bit. And I'll scroll down past the proof that the nth convergent really is modeled by Pn over Qn, where again, Pn is this and Qn is this. And I just want to give you a little application down here about, let's say I wanted to figure out the continued fraction for pi. And, you know, pi is a pretty nasty, irrational number, pretty unpredictable. And so let's say I specify some bits here, or I don't, but the book does. So maybe it chops it off here, say. So Sage has some built-in commands in order to just tell me what the convergents actually are. And so they're right here. And all I want to do is just kind of illustrate what's going on here. So what this one would be, this 3 should be equal to P0 over Q0, because it's in that spot there. And as far as P0 over Q0, if I go back up to my formulas here, well, P0 should just be A0. So here's P0 and here's Q0. P0 should just be A0, and Q0 is 1. And now if I just look at my fraction, A0 is the 3, right? It's the first entry in my partial fraction. And so that's how we get 3 over 1. So I've told you something incredibly deep. 3 is equal to 3 over 1. So all I'm trying to do is just illustrate again, how do we obtain this formula here. So similarly, let's say, where does this 22/7 come from? So this 22/7 is what allegedly P1 over Q1 should be, but let's just make sure that that's the case. So P1 over Q1, if we look through, now we're going to use this part. So P1 should be the same thing as A1 Q0, right? We're plugging in 1 for all the n's that you see here. And so A1 P0 plus P sub negative 1, and that's divided by Q1 should be A1 Q0. I think I set a 0 here earlier, and then I meant to change it. A1 P0 plus P negative 1, and then here should be A1 Q0, same thing, and then plus Q negative 1. And now let's go back and plug in the things that I actually know. And so let's see, I still know that P0 is just 3 according to this. And I also need to know now that so let's see, what am I telling you here? I know that A1 in this case is also 7. So this should be 7 times P0, and P0 we said is 3, plus P negative 1. P negative 1 is just 1. And then that's where you see that's to the 22. And then in the bottom, A1 is 7, right? Remember, this is in the A1 spot because 3 is in the A0 spot. 7 plus Q0. Q0 is defined to be 1. So 1 goes right here. So 7 times 1 plus Q negative 1 is right here, and that's defined to be 0, so plus 0. So that's where you get the 7 from on the bottom. So this is where the 22/7 comes from. And just to say a little bit, and you probably guessed that this is what's happening though, if I look at these partial convergents individually, and I'm thinking about, well, 3 is pretty close to the number pi, right? The number that we're approximating here. 22/7 is pretty close to 3.14, blah, blah, blah. And so what each individual entry in the sequence of partial convergence is it's a pretty good, in this case, rational approximation to that number. And it turns out it's rational in this case just because the a's that we're playing with were all integers. And remember, there's nothing that says we have to be using integers here, just in this specific example we do. But in that case that we are using integers for the a's, then your fractions, p's over q's, they should all be good rational numbers. And what you should also expect is as you go further and further out in this sequence of partial convergence, that you should be getting closer and closer to the number pi that the continued fraction is representing. And just to scroll down a little bit as well, one other question that you might have is, do these fractions ever simplify anymore? And that's answered a little bit later on in corollary 5.2.10. In the case that these things are simple continued fractions, and remember all that means is that each ai is an integer, then when you look at each individual convergent, they're always in lowest terms. Those are always simplified as well. And so again, just to recap, we looked at taking a continued fraction, but then just kind of cutting it off, chopping it off, and we'll call that the nth convergent.